them as maps. Okay, so the first thing is to compare with geodesics. But basically what happens is that for geodesics, everything will be very nice, and then not so nice anymore for pseudo-holomorphic curves, okay? So what are geodesics? So these are paths gamma from some interval in R to your manifold, which now is a Riemannian manifold, okay? And they locally minimize length, which is basically the integral from A to B of gamma dot dt, right? So you integrate the velocity, right? V dt, and then from A to B. But they are critical points of the analogous energy functional in one dimension, which is the energy, the integral from A to B of gamma dot of t square dt. Okay, so they are critical points of these things. So they are critical. So the first thing you want to do is to see how does the energy control the map, this map. So you can look at, for instance, you take any 2 points, let's say S1, S2. Let's say that S2 is bigger than S1, so let me put like this maybe. In AB. And you look at the distance from gamma S2 to gamma S1. So what is that? That is the integral from S1 to S2 of this thing, right? Gamma dot dt. Let me give it a bit more space here. Okay, and now you can use Cauchy-Schwarz here, and you can think of this as the function constant equal to 1 being integrated against that other function. And then if you use Cauchy-Schwarz, that is S1 to S2 dt to the 1/2, and then the integral from S1 to S2 of gamma dot of t square dt to the 1/2. Okay, so that's Cauchy-Schwarz for the L2 inner product, right? So here is the function 1 square. And so this is basically S1 minus S2 to the 1/2. And this thing here is the energy, right? So it's less or equal than the energy, this thing, because the energy is obtained by integrating from A to B, and S1 and S2 are inside there. So this thing gets less or equal than the energy of gamma to the 1/2. So the point is that for all S1 and S2, the distance from gamma S1 to gamma S2 divided by S2 minus S1 to the 1/2 is less or equal than the energy. So the energy controls this quotient. And the supremum over all S1 and S2 of this quotient is the C0 1/2 older norm. And so this gives a bound on the C0 1/2 older norm from a bound on the energy. Okay, if you don't know what the C0 1/2 norm is basically this thing, the supremum over all S1 and S2 of this thing. And why is that good? So the reason why it's good, is that now suppose you have a family of curves, with a uniform bound on their energies. So the energy of each element of the curve is less or equal than a constant that does not depend on I. So that's what I mean by uniform. Does not depend on I. Okay? So then, So if you have a family of such curves, then this computation tells you that there exists a uniform bound on C0 1/2. If this doesn't tell you nothing, then jump this step and just look at the next one, which says that this bound here, or this thing here, tells you that this family of curves is equicontinuous, is equicontinuous, as maps from AB to M, okay? And then if it is equicontinuous, you can use the Ascoli-Arzelà theorem, or Arzelà-Ascoli, to say that there exists a uniformly convergent subsequence. Okay, so, and that is basically what compactness means. Okay, so you have a compactness here. I'm thinking of it in the sequential manner, right? You take a sequence of points, arbitrary, and you want to know whether there is a convergent subsequence or not. Okay, and this is so, and this elucidates, I think, the key properties you want to do in order to get compactness. I saw this example from Simon Donaldson in his paper in the notices, and it's because usually these things with geodesics are made with finite dimensional approximations, like in Milner's book on Morse theory for the length for this energy functional. Then this is all done with finite dimensional approximations. But this elucidates very much what we do in order to get compactness in other analytical problems, which is to get uniform enough control in some norm that guarantees by some compactness theorem like the Ascoli-Arzelà that there exists uniformly convergent subsequences. So if you have seen things like that, like this, what replaces usually the Ascoli-Arzelà theorem is the compactness of some Sobolev embedding. Okay? And this is more or less the strategy also for holomorphic curves, except that you don't have compactness in such a nice manner as this. So you need to figure out how do you lose compactness first. And to do that, I'll do an example, which is supposed to tell us what are the key things that can happen and that a general theorem on compactness needs to explain. Okay, so we will see in this example a few features that our theorem on compactness will have to explain. So the example goes as follows. So let's take sigma to be CPU1 and also take M to be CPU1. Okay? And then equip each of these with the Fubini's 2D metric. So omega sigma is I over 2. So in homogeneous coordinates, so if you think of CPU1 as C union infinity, then this is dz wedge dz bar divided by 1 plus the norm of z square. I'm just writing this so that I have everything on the board, okay? In case I need it. And I will. I over 2, and I'm going to call the coordinate on M W rather than Z. dw wedge dw bar, 1 plus the norm of W square. Okay, and then let's take a map from sigma to M. Let's call it U infinity. A map from sigma to M, which is just a map from CP1 to CP1. So and I want it to be holomorphic, so it's going to be a meromorphic map. And let's say it has degree n. Okay, then it's already an holomorphic map. Okay, I'm taking an holomorphic map of degree n. So it's a meromorphic function. And I want U infinity of 0 to be different than infinity, okay? This is just so that, I mean, yeah, you can just move things around so that this happens if you want. Okay, so that's, And now from this, I'm going to construct a sequence of maps. Now consider the sequence UK, not U little k, from sigma to M, given by UK of Z. I'm going to write this as 1 over k times 1 over Z plus U infinity of Z. Okay? So as k increases, this thing away from 0 becomes smaller and smaller. Okay? And they start look more like U infinity. Okay? So away from 0, this thing will disappear when I send k to infinity. Right? If you work away from z equal to 0. So that is the first feature. Okay? So that as the away from some finite set, which is just the point 0, the UK is converging to U infinity. Okay? And converging in which way? Uniformly on compact subsets with all derivatives. Okay? Then the second feature is that this map U infinity, which you obtained, so of course I started with it, but let's forget I started with it. You obtain it here as the limit of the UKs away from that point. And this map U infinity actually extends across those points. Okay? U infinity extends across S. That is obvious in our example. Okay? So this I would summarizing in words in some shells, if you want like to put things in shells. These I would call converges away from the blow-up locus, and blow-up locus is S. And these I would call removable singularities, okay? Which we already proved. Well, we didn't prove it actually, so which we already mentioned. But there is a further phenomenon, which is the fact, notice in fact that the energy of the UKs, of U infinity, is less or equal than the energy of the UKs. In fact, we can compute it. The energy of the UKs, so they have, if U infinity has degree n, the UKs have degree n plus 1. And so these have energy, it's basically pi times n plus 1, okay? Because pi is the area of CP1 with respect to the Fubini study metric. And then this is the degree of the map. And this U infinity has energy pi n. So in our case, in this example, that thing is actually smaller. Okay? So we lost energy. And you may ask, where did the extra pi of energy go? So where did the extra pi of energy go? And the point is that somehow it got concentrated on 0 and escaped through there. Or we would say bubbled off there. Okay? And so that is more or less the answer. We will see it in a second. That's why I wrote this thing, so I can do some computation. And you may also want to find a way of recovering it in the form of a map. You want also to recover some map which accounts for it. It's like when bad things happen, you like to blame someone for it. And this is also, in this problem, we do it. Anyway, so let's see. So the idea to do it is to try to rescale at 0. But first, let's see. First, I told you that it gets concentrated at 0 and escapes through there. I need to justify that thing, so I would better compute the energy density, say, at 0. Okay? So if I want to compute the energy density at 0, I want to compute the norm of du k square near 0 And this thing is UK star omega m divided by omega sigma. Okay, that's an easy way to compute it. There may be other ways, but that's what I think I'm going to do. And I'm going to write UK as, so near 0, it's basically this thing that dominates. I'm going to call this VKZ. And then there is this other map, which, as I said, that U infinity of 0 is different from infinity, then this thing is going to be bounded near 0, okay? And as k gets very big, well, even when k doesn't get very big, anyway, near 0, this thing is exploding, right? So this thing is what dominates. So up to first order, this UK star omega divided by omega sigma, given that I'm looking near 0, this is basically VK star of omega m divided by omega sigma plus lower order terms. Okay? So let's do it. So now, if I want to pull back omega m by Vk, I need to replace in this formula the W by the Vk of z, which is 1 over kz. So in the numerator, the dW becomes minus 1 over k, 1 over z squared dz, and the dW bar becomes minus 1 over k, z bar squared dz bar, and then that w squared over here becomes k to the minus 2 mod z to the minus 2. Okay, so I'm going to replace that there, and we get I over 2, 1 over k squared, 1 over the mod of z to the 4. I'm already putting them together, dz wedge dz bar. Right? I'm already putting this guy together with the bar of it. You get k squared mod z to the 4. And then you got to divide this by 1 plus the norm of, k to the minus 2 mod z to the minus 2 square. And then you divide by I over 2 dz wedge dz bar divided by 1 plus norm of z square. Now I just copy down omega sigma plus lower order terms. And then this thing is equal to, so you cancel these things and also these things, and you get 1 plus mod z square, 1 plus k to the minus 2 mod z to the minus 2 square, 1 over k square, and then 1 over the norm of z to the 4 plus blah, blah. Okay? Now you pass this norm of z to the 4 inside here, and you get, so let's see, we have norm of z square plus 1 in the numerator, square. Now you pass this thing inside, you get a norm of z square plus k to the minus 2, everything square, 1 over k square plus lower order terms. And near 0, when you put z equal to 0 here, you get 1. You have k to the minus 4 there, because minus 2 times 2, and then a k squared. So this looks like k squared plus something like that. And that goes on, right? So, in conclusion, if you look at duk at 0, that thing is k. I had a square there, I took out a square, and you evaluate at 0, you really just get k. Okay? So that is k. And this is going up to infinity as k goes to infinity. So indeed, as I promised, the energy density is getting concentrated at 0. And how can you try then to do the second part of finding a map that accounts for this extra pi of energy? And what you can do is to rescale by this number. Okay? So you rescale by it. So now you rescale. Of course, where do you rescale? Around 0, which is the point in S. With the norm of duk of 0, which is k. So you define another map, which is the rescale at 0, element of the sequence k of z is equal to uk z divided by k. Okay, so at 0, because if it was, let me write at 0 so that it is clear, 0 plus z divided by k. Okay, so that it is clear that I'm rescaling at 0. And what is this? Well, we have a formula for uk, is this thing. So now I have k, now z divided by k, the k's cancel, and I get z over k there. So we get, that is 1 over z plus u infinity of z over k. And so, and near z equal to 0, or maybe not even near z equal to 0. So, so when you divide this by k here, then u infinity, as k increases, its poles and zeros and so on will move more and more far apart in C, right? They will be pushed apart as you rescale by k. So in larger and larger portions of C, these maps resemble more and more the map U at 0, so it's called the bubble at 0, 1 over z. Okay? This is in larger and larger portions of C. But you can think of C as being contained in C unit in infinity, which is CP1. And of course, this map extends across it. Okay? So you obtain I mean, maybe when I prove this thing in the general setting will look easier. But anyway. So you obtain a map U0 from CP1 to CP1 with the other pi of energy. So this is called the bubble at 0. And so C is that there exists a pseudo-holomorphic sphere bubbling off at 0. If I get time to state this precisely, I will. And if I have time to show you how you obtain that holomorphic sphere, I will also show it. Okay? But anyway, so now what I wanted to do is that I wanted to keep in mind A, B, and C. And now I'm going to write a theorem, which is the main compactness theorem, which explains A, B, and C in the general setting. Okay, so theorem. I may have to erase A and B, okay, because it's a long theorem. So you take a sequence of maps, a sequence of pseudo-holomorphic maps with a fixed, whose image is fixed in cohomology. By the way, before I continue, let me make another note, because you have probably been hearing a lot about holomorphic curves in the other talks yesterday from Marta and Joe, and also you will hear it again, at least from Vinicius. And I think they work mostly with non-compact curves, and I'm doing everything for compact curves. But it's because it's easier for compact curves, so I figured I would do it for compact curves. And also, if you want to extend these theorems to non-compact curves, then you need to add more conditions or put more adjectives on the statements, like finite energy and things like that, okay? But I don't know all the details about that. Okay, so now here I pick a sequence of pseudo-holomorphic maps with fixed homology class, then a up to a subsequence, up to passing to a subsequence, the following happens. A, there exists a finite set, so a finite set of points, such that UK converges to, so there exists a finite set and U infinity away from that finite set, such that the UK converges to U infinity uniformly with all derivatives on compact subsets of sigma minus S. Okay, so there is this set. It's a bad set where you don't have convergence, but it's quite small. It's just a finite number of points. It's as small as it can be. Okay, smaller than that only if it was empty, which was the case in geodesics. So okay. And then B, remember B was the removable singularity, so U infinity extends smoothly across I'm starting to lose all the words when I write. So that happens. U infinity extends smoothly across S to a pseudo-holomorphic map. U infinity from sigma to M with energy less or equal than the energy of the UKs, which was fixed, remember, is omega evaluated on beta. And C, I will not write a precise statement now. There exists a pseudo-holomorphic sphere bubbling. For all, so C says, sorry, for all x in S, there exists a pseudo-holomorphic sphere bubbling off along S, around S, around X. Maybe, yeah, so maybe I'll say the precise thing here. Then, so what it says precisely is that, but I will not tell you how you get these sequences. That's for that you need to check the proof. Is that there exists a sequence of points xk converging to x and a null sequence delta k going on to 0 such that the map uxk of z, or the maps defined by, you look at uk and then you exponentiate from x delta k times z. So these maps uniformly converge with all derivatives on compact subsets of C They are defined in larger and larger pieces of C because delta k is a null sequence. So that means you can let this Z be bigger and bigger and the exponential will still be defined. Okay? Compact subsets of C to a pseudo-holomorphic map, which is the bubble UX from CP1. So C, you see C inside CP1 as before. CP1 to M. Okay, so this is the precise statement, and this is quite similar to I think, to what I constructed in that example. Okay? So now let me try to explain a little bit about why is it that these things are true. Okay, so I will not call it proof because I'm not going to prove everything, but I'll tell you why each piece of that, a little bit about why each of those things are true. Okay, that may take the rest of the whole time already. Okay, so let me call it. I'm trying to answer why or convince you why that is true. And so let's start with A. Maybe before that, let me say what is the main analytical estimate, the main estimate you need. The main estimate you need is a way to control the map from its energy locally, okay? And that is a result called epsilon regularity. Which basically says that there exists an epsilon naught and a c greater than 0 such that for all pseudo-holomorphic maps and points in M, or maybe in the image of the map so that it makes sense what I'm going to write after, but anyway. If the energy in a ball, so a disk of radius 2r, so x is a point in sigma. In the disk of radius 2r around sigma of du square divided by 1/2 is less or equal than epsilon, which is strictly less than this epsilon 0, you should think of epsilon 0 as being very small. So if locally the energy is very small, then you can actually control the supremum of the energy density just from the local energy, okay? You can control this thing from its integral, okay? That of course uses the equation, uses the fact that U is pseudo-holomorphic, okay? So let me, that of course uses that, okay? So then the supremum of the norm of du square in a ball in the disk of radius r, a smaller radius, is less or equal than c divided by r squared, the integral over d2r of x du squared. Okay? Okay, so yeah, I need to be careful with the 2 so that all the results appear with nice constants. Okay, so that is the main analytical estimate, and once you have it, you can try to use an integral version, by integral I mean with integrals, so not pointwise version, of identifying the blow-up locus. And the blow-up locus is this bad set where there will be no convergence. So you saw from the example that this bad set is the points where the energy density accumulates. So if you want to identify it, maybe the best way to try to identify it is to try to look at it as the set of points where this thing fails, where you don't get a way to bound the supremum norm, the pointwise norm of the energy density. So you want to identify it as the set of points at which this fails, okay? And you want it to fail for all small r. You want it to fail for r as small as you take. So that's how you define the blow-up locus. So let's define S. So far you still don't know that this S is the same S that I'm talking about here, okay? But it is, so I won't give you another name, okay? So it's the set of points in sigma such that that condition fails. So okay, of course, now remember, in this theorem we have a sequence of maps. In that theorem we only have one map, okay? So now we take a sequence of maps, okay? Take a sequence. as before. And you want to identify the blow-up locus of the sequence, okay? So if you want to take the limit, you want this thing to fail as you take the limit when k goes to infinity, okay? So the sequence is labeled by k, okay? So the way you do that is that you want that thing to fail, so you want to take the if, which is the smaller of the limits that you take as k goes to plus infinity of the integral over d 1/2 2r x duk square is greater or equal than epsilon naught. Okay, so that means that thing is failing. And as I said, you want it to fail for all very small r. So you take the intersection of these sets over all r greater than 0. Okay? So it doesn't matter how small it is the disk you integrate, this thing is getting concentrated. Okay? This thing is going up. So this means in particular that this thing here, the integrand itself, as you take the sequence, gotta be going up. Okay? Gotta be exploding. So you do this, and then the first result, let's call it a lemma, says that this guy is finite. Okay? This finite part. That this is finite. And the way you show it is finite is to give a bound on his zero-dimensional Hausdorff measure. So the result says the zero-dimensional Hausdorff measure of S is less or equal than epsilon naught to the minus 1 omega b, which, remember, is the energy of the sequence. Okay, so this is the energy of the sequence. Okay, let me also write that here. So E of uk is beta omega. Okay, because of this condition. I'm assuming that the image lies in a fixed homology class. Okay, and why is this true? So it may not be clear as I start where this is going, but it's not very long. So you will soon be able to put together the first things I do, okay? So I'm going to take a cover of S, which is a very stupid one. I'm just going to take balls. So I'm going to fix a delta, and I'm going to take the balls of radius delta around each of these points, okay? So I'm taking the union of balls of radius delta around all the points in S. This obviously covers S, right? Because all the points of S are contained there, are the center of the balls. Covers S and covers a lot more, right? So, and then you use Vitalis covering lemma. What does that say? That says the following. There exists a countable subcollection of these balls. So I'll given that they are labeled by their centers, I'll call it a countable subcollection of centers, xi, with I in some index set, which is countable, such that the balls are pairwise disjoint. So this is empty for I different from j, okay? Of course, right? So that is empty, but S is still contained inside the union of over all I in I, not of these balls, but of rescalings of these balls. So d 5 delta of xi. So these balls are pairwise disjoint, but they are such that if you keep that number of balls and you scale them up, you still cover everything. So let me make a picture. So of course S is a finite set, so it's not this thing, but let's say it was something like this. Then you have these balls that are pairwise disjoint. But of course, if you take them 5 times bigger, they will cover everything, right? Because this is, for example, this 5 times that ball, 5 times that ball, and so on, okay? I think Vitalis covering lemma is not with a 5, it's with some other number, but that some other number is less than 5, so 5 is okay. I don't remember exactly what is the best
thing that you can probably do there. I don't know if that is known. Is that known? What is it? It's 5? Okay. 5 because it's countable and not finite, right? Something like that. Anyway, so we have that, and now, given that we have this cover, we can start trying to bound the zero-dimensional loss of measure. What is that? What is the zero-dimensional loss of measure? So the zero-dimensional loss of measure of S is the limit as delta goes to 0 of this other thing, which I'm going to tell you what it is, okay? So I'm not... So that other thing is what? Is the infimum over all covers of S of the following number. The sum from I, sum in I, of the diameter of these sets, of some sets ui to the power 0, because it's the zero-dimensional. If it was the k-dimensional, you would have to the power k, such that the ui's, the union of the ui's covers S, and their diameter of the ui's is less or equal than delta. So you compute this thing, this infimum, for all delta, and then you take the limit as delta goes to 0, okay? So this is basically, you are trying to cover S by as small sets as you can, and then take their volume, okay? This is the zero-dimensional volume, okay? So in this case, how do you do it? So in this case, you have H naught delta of S. Well, it's an infimum, so it's less or equal than whatever I'm going to compute using this cover, okay? So this is less or equal than the sum over all I in I of 5 times delta to the power 0, which is just sum over I in I of 1. But remember, these points xi are in S. And if they are in S, this happens, right? And this happens if they are in S. So you write this instead with deltas here. So let's say you have, maybe let me redefine this in this way and write this result with R here and R over 2 here. Okay, it's just so that everything pairs nicely. Okay, I did not just cheat you. I just divided R by 2, which I can because R is an arbitrary number. Okay, so if these points xi are in S, then you know that 1 is less or equal than epsilon naught to the minus 1 times the limit as k goes to infinity of 1/2 the integral over the d deltas of xi of the energy density of the UKs. Right? That's it. You know that. So I can replace that one by this thing. So this is less or equal than epsilon naught to the minus 1 sum over I in I of the limit as k goes to infinity of 1/2 of the integral over d delta of xi of d UK square. But now remember, these d deltas are pairwise disjoint, right? So if I'm summing this, let's pass this sum over here. So this thing here is integrating the energy density over a set that doesn't even cover S. So doesn't cover the whole manifold, doesn't cover sigma. So you can bound these by above by the energy over all of sigma, because these guys are disjoint. Okay, so you don't get redundancies, they don't intersect. You don't get a redundancy by bounding these by above by the energy over sigma. So this is less or equal than the integral over sigma of the duk squares, and then you take the limit, but this thing here is less or equal than is equal to beta of omega is fixed. So you get here that this is less or equal than epsilon naught to the minus 1, omega beta, sorry. Right? That's why it is important that they are disjoint, because then here you can just replace this by something that is bigger, which is the integral on the whole manifold, and that, you know, it's bounded by hypothesis. Okay? So this shows that this H naught delta is less or equal than this, but of course this does not depend on delta. Okay? So you can take the limit when delta goes to 0 of this thing, and you get the same thing here, less or equal than epsilon naught to the minus 1 omega beta, and that gives you the result. Okay, so that's basically how you prove this part. So it's relatively easy if you are willing to draw some balls. Okay, it's not that complicated. Okay, so that's why this is a finite set. But I didn't yet explain. Now I've erased it. All the things that are in A. A also contains the convergence away from the blow-up locus. And that is, I mean, I'm not sure how happy you are with seeing this analysis, but I prepared to do a bit of the analysis of that. I don't know if you are willing to see that, but I could move on and talk about the transversality, which is useful also for you in the remaining time. What I can either show why convergence away to the blow-up locus works now, or and then talk a little bit about the bubbling, how it works, or I can go and say a few words about transversality.
Can you say some words about transversality?
Okay. Okay, but that is easy to find in the internet, other videos that say that. Anyway, I will say some words about transversality, but it's a part of my talk that I prepared less. But anyway, so it's fine. Transversality. So I'll be, well, if you want, I can maybe show the rest maybe later in the afternoon if that is willing. And now I'll say a few things about transversality because they probably need it for their talks. But anyway, so about transversality. So for this, let's go back to the definition of a holomorphic curve, and let's regard the Cauchy-Riemann operator as a section of a certain vector bundle. So what does it do? It eats maps from sigma to M, right? So these are maps from sigma to M, and it takes values in some vector bundle whose fiber at some map U, Tu, is what? Is sections of T sigma tensor U star of Tm, right? Because del bar J of U is a section of this bundle. Do you remember this? This was in the beginning of the talk. Okay? So now, and if you want to construct something like the moduli space of holomorphic curves, then you need to, under certain conditions, look at when does this section intersect the zero section of this bundle. Okay? So you want to look at the preimage of 0 of this section. And if you want to show that a manifold that you define in such a way is smooth, that section better intersect the 0 section transversely. Are there questions? No? If you want to pose, sure. TM. This thing here?
A tangent bundle, not tangent bundle to sigma, no?
Oh, yeah, yes, you are right. Thank you. Very good. Thank you very much. Yes, that's right. Because, so del bar J, it was computed from du, and du is a map, remember, from T sigma to U star of Tm. and then it's a section of sigma T star sigma tensor U star of Tm. Okay, so that's right. So this here is a T star sigma. Okay, so, but I was saying, so if you want to look at some moduli space, so I'm going to draw also infinity sigma m here as something like that, and then this bundle is something like this, T, and this is the fiber over some point U, and then you have this section, which is something like this. Of course, to define the moduli space, you need to put more conditions on the curves, but you want, what you would like is that if you have a U is a point here, if you have a U, you want it to intersect the zero section transversely. And what does intersecting transversely means? Means that the derivative of this map at that point U, if you project it on the fibers, that needs to be a surjective map. Okay, so that's Sartre's theorem. No, Sartre's theorem says that such points exist, so that's just linear algebra. The inverse function theorem. Anyway, but so let me tell you why is it that, how is it that you can, suppose for now that such map intersects the zero section transversely. Suppose for now that del bar J intersects. So how do you write this transversely, the zero section at U? How can you compute the dimension of the moduli space of holomorphic curves near that U? You can compute it as by looking at the dimension of the kernel of the derivative of that map. Okay? So that's, but of course in general it could have co-kernel also. But, so what in general you would like to do is to compute the index of that map if it was Fredholm between certain function spaces, which it is, and then find a way of making perturbations so that this map in fact intersects transversely, and that you may not be able to do always, I don't know, but under certain conditions, which is these curves being simple, you can. So let me first tell you how do you compute the index of that map. So the idea is that if that is the case, then locally, the dimension of the moduli of curves near U is equal to the dimension of the kernel of the derivative of the map del bar J at the point U. Okay? And now what I'm going to say is that there exist Banach space norms I promise not to write down a Sobolev norm, so I'm not going to say what they are. Between this thing and this thing, on those things, such that the map du del bar J is Fredholm. So this is in general. This is in general. So not only in that case. And then you can try to compute its index of this thing, which is equal to the dimension of the kernel minus the dimension of the co-kernel. And how do you do that? You need to compute that derivative. And if you compute that derivative, I mean, it's not hard to do that computation, but I'm just going to write what it gives. So if you compute du of del bar J, that is basically del bar j, but now at u, okay, j at u is a fixed, almost complex structure on the target because it always lies around u, plus some algebraic operator. This is algebraic. So meaning that it takes no derivatives. And if it is algebraic, that already hints that somehow this guy is gonna contain all the information on the index. And that is in fact true because you can prove this thing is compact for the choice of Banach spaces, which I did not tell you. And then, given that the index is invariant by compact perturbations, the index of du del bar j is equal to the index of del bar ju, which is just a map on sections of a certain bundle on the curve, and you can compute this from Riemann-Roch, which you can compute from Riemann-Roch. And let me see if I remember the formula. So it gives you n times the Euler characteristic of sigma plus 2 times the first Chern class of Tm j u of sigma. Okay, so the first Chern class eating that. That's how I have been writing things. Okay, so okay, and now and then the thing is, so now you want. So in order to make this piece here work, you need to say that there is no co-kernel. And when is there an example when there is no co-kernel? So if u from sigma to m is such that u minus 1 is such that there exists a point p in m such that u minus 1 of p, so let's say u minus 1 of p is just p, and the derivative of u, okay, so that I should say rather in the points in the target. So let's say x in sigma such that u minus 1 of u of x is just x, and du at x is injective. So this is what's called a somewhere injective curve. And J is generic, meaning that if your J doesn't work, perturb it a little, and with big probability it will. Then there is no co-kernel. And under those conditions, the moduli space around U is smooth. Okay, so that is the transversality result, I guess, right? So that's it.